So today we'll discuss about the use cases for multiple protocols, and we'll see how exactly the Tacacs and Radius works, and we'll see the flow of Tacacs and Radius, and we will discuss about some use cases for Tacacs and Radius. So let's get started with that. So the first thing, we tried IP accounting last time, and so when I made a research, actually, we can only do an accounting for the hardware packets. So the users can see the number of packets that's been sent and received in the Cisco iOS, and that is the whatever the traffic that is generated by the software, or it is, if it is generated by the iOS, that cannot be captured. So I'll give you a background about that. So any switch, a router these days, we all know it got a ASIC chip. So inside this, all your information will be saved. So example, if this is your switch, any vendor switch, if it is with an ASIC infrastructure, because it's all hardware switch now. So all your data plane traffic will be handled by ASIC chip. So along that, what are the informations you see inside the ASIC chip? So you got your FIB, your forwarding information base, and your TCAM table, your MAC address table. So this is typically a hardware switching chip. It is used. And if you go for any kind of Nexus devices, that is called a distributed memory. We are not going to detail about that. So here, IP accounting, you can monitor the traffic only if it is going through the ports and if it is hardware switched. So in Cisco, there is a global command, IPSec. That is called Cisco Express Forwarding. It's nothing. It is used to save your cache information. So say, for example, you got your RIB, your routing information base, and you got a route for the same network. You got a route for, you got OSPF and your EIGRP, it's running. So the routing table will always have the best route. So if I got a route for the same destination using OSPF and EIGRP, so it's going to prefer EIGRP. It's based on the administrative distance, and this particular information will be, it's being placed inside the routing information base. And FIB, so whatever the most frequent accessed information. Example, if I want to reach a specific destination, and if my egress port is GI0/0 and my request is coming from GI0/2. So this particular information will be saved. So for all this 10 networks, so my egress port is, for all my 10 network, the egress port is GI0/0, 0/1 example. So all this information is cached. So the most frequently, and if it if the same type of traffic and for the specific destination, then this particular information will be saved in the fib. So that is kind of a cache. So it doesn't want to look for the RIP every single time for the train network because I have this information in my fib. So all this information will be in the ASIC chip. So what I'm trying to say is the IP accounting information. So what is the source and destination that is used, and what is the number of packets that's been sent, and what is the amount of bytes. So all this information will be saved only if it is hardware switched. If it got an ASIC, so it should be in a hardware appliance. So we are using a GNS, so it is just a simulator. So we do not have an ASIC chip inside. We're just simulating the traffic. So that's why we couldn't find it. So that's the document here it's talking about. So only transit IP traffic is measured in only on the outbound basis because it is a command for IP accounting output packets. And the traffic generated by the software or terminating the software is not included in the accounting statistics. So it should be in hardware appliances to do that because we have to have an ASIC chip to do that. So here we do not have an ASIC chip. So I tried by removing the access list and I'm allowing all the IP traffic, but still I couldn't find it. So when I did a little bit of research on it, so I come to know. So we have to have an ASIC chip, and it should be in hardware appliances for IP accounting. So it should work in the real appliances. It's pretty simple command. So wherever you have your IP config, your layer 3 ports, your octet ports, you have to give this particular command. So IP accounting output packets. So if you want to match a specific traffic, you can use IP account list and you can give your destination IP. So you can match your source and destination IP details to see that. And also if you do a little bit more research on IP accounting, you can also validate your ACLs. So is it how many hit counts you see in your ACLs, and is it your ACLs is being used? And if you're applying a specific access group for a particular interface, you can still log all this information here. So if you got your access group configured here, you can still log all your traffic using IP accounting. So you can go through the document and you can, play around with that. So that's about IP accounting. So you cannot get that in GNS. Hi, Imran. Yeah, we discussed, today we are discussing about Tacacs Radius and the most used protocols and use cases. These are all the topics we are going to discuss today. And the next topic is the use cases. We'll jump into the use cases. So by looking into the capture, and if I see for LLDP, this is a layer 2 protocol. And what are the key informations I'll see inside the LLDP? So the key information inside the LLDP is LLDP is a layer 2 and it is used for it's an IEEE standard. So any vendor can support this LLDP. So all you have to give is LLDP run, and inside your LLDP you will get to know about your source MAC, destination MAC, and apart from that, what is the port it's being used, what is my source port, and what is the destination port. You'll get to know about all this information. This is very important. So LLDP, I'll go back to this. So we all know about that, but again, so I'll give a background about that. So when you got two appliance, any two boxes, so on the wire, so using LLDP and CDP Cisco proprietary. So in Cisco, in CDP, I have seen, we share the VTP information, VLAN trunking protocol, and we know about the source port, destination port. All this information is locked, and in the same way for LLDP, also we know the source port and the destination port that's used, because that's very important. Because if you connect any VM servers or any Windows server, something like that, and if it is capable of running LLDP, so you'll get to know about the neighbor port. Because from remote, if you access, you will come to know, okay, this particular port, fast Ethernet 0/1 is connected to fast Ethernet 0/1 on the remote port. So you know your source local interface. And your remote interface. So what kind of port is that? It is a gigabyte port, or it's a 10 gig port. So what kind of appliance is it? Is it a VMware, or it is a Windows machine? So I'll get to know about platform level information and where exactly I receive the MAC address for this particular port. So you'll get to know about all this information in LLDP. So it's link layer discovery protocol. So both end has to run the LLDP to get all this information. So this is very good when you work from remote. So you can build the topology and you can find what are the kind of config and what is the conflict you have with that. And we all know this is very familiar protocol, EHRP in Cisco proprietary. But when you look at this, inside this EHRP, you will know what is the EHRP version it's been used and your checksum is validated or not. So what kind of EHRP packet is that? So from just giving the EHRP in the display filter, you'll get to know about every single EHRP conversation here. The key thing you should know about is, okay, I send a hello for my multicast address. So it's one-to-many. This is my source router, and this is for my destination multicast. So everybody will be listening to this hello. And we discussed about this thing, ARP. We know to reach a particular destination, I have to have a destination MAC address. And if you look for your ARP request, on your layer 2 is always layer 2 flooding. It's all F. That is your layer 2 broadcast. It's a broadcast request. And so this is a Cisco appliance. And from the layer 2 header, you come to know, okay, so what is my next protocol using this? We call this an ether type. We discussed about that. So for every protocol, there is an ether type option. So this ether type option 0x0806 is used for ARP. So if it is for IP, it's going to say it's an IP. So my next request is ARP reply. So that is the meaning of it. So for my ARP request, I have to get an ARP reply back. So it is asking for who has a destination MAC address for 192.168.1.115. And it is trying to reach its own gateway, 192.168.1.249. And I get a reply back for it. This is ARP resolution. And if you see the sender MAC is an Apple device, and it is the IP address of it. So you know the target MAC address. If you look at this, so 135, and this is gprocom. And you get the destination MAC address. So if for your ARP request, you have to get an ARP reply back. So if you see from the ARP reply, you get the destination MAC address here. So for ARP request, you should get an ARP reply back. And the next protocol is my IPv4. So from layer 2, it is an ARP packet. And then after the ARP, I'll get an IP address. So that is OSI reference model as well, layer approach, layer 2, and then layer 3. So the next protocol is IPv4. So I got my ARP reply back. So what is my next communication? It's my layer 3 headers. And the other thing, this is important. This is a dynamic trunking protocol. This is used for the switches. So once you have your switches connected, something like this, you got 2 switches. And if I configure this particular port as a trunk port, so we know we are tagging all the VLAN information. All the VLANs are allowed if it is trunked. And this is vendor specific. So for some vendors, you have to tag the VLANs independently. And say, for example, if I got VLAN 2010, 2030, so if I do a trunk, so DTPs by default, it's enabled. It will be a DTP port. So it will negotiate for a trunk port. So it becomes a trunk and it's going to receive all the VLANs here. So again, this is vendor specific. If DTP is not enabled or if a DTP is not working, so I'm talking about Cisco iOS. And if it is other vendor devices like Juniper, the principle might be different, but I haven't worked on it. But the logic is DTP is a dynamic trunking protocol. So what are the VLANs you're allowing? So this dynamic trunking protocol is something, it's a dynamic, and if you make it as a trunk on one end, so I'll negotiate for a trunk port and both becomes a trunk port and it receives all the VLAN information that's been sent from the remote switch. So that is DTP. And inside DTP, you will know what kind of tagging it's used. It supports 802.1q and it's an IEEE standard. So what are the VLAN information you send? I can understand and I will forward the same. So that is 802.1q. So when you drill down this particular information, it says trunk administration status as on. So it means that I'm receiving all the VLAN information, whatever you send. And as I said, in the DTP, if you define your domains, that comes under VTP. In Cisco boxes, we configure the VTP domains, that is VLAN trunking protocol. That is something we use as a client and server to exchange the VLAN information instead of doing the VLAN configuration every switches. So you can make one as a server and others can be a client on transparent mode. So that depends on the scenario. So that is all used for, you can see this information, and if you can see your trunk port status, is it active, and what kind of trunking protocol it is allowed. So there is two key points you have to consider, that is trunking is enabled and what is the protocol I'm negotiating to. It is 802.1q. And CDP is an equivalent, and it is used for Cisco boxes. And here in the same way, I know the Cisco version, the platform, and what is the port ID that's used. This is a building block for your layer 1 connections to your nearby devices. So with this, you will have a complete insight about what is connected and what kind of device is it, what is my uplink and what is my downlink. So you see this is device ID and this is a port ID. So I receive a traffic from, so you'll get to know about all this information here. And STP, it is a standard for all the switches. It's to avoid the loop avoidance. So here we see what kind of STP that's being used. And you see this BPDU packets where it goes from learning, listening, and forwarding. So it should be in a forwarding state to send your active traffic. And designated port is your your port that points to your route, and you know about your bridge ID and all this information, and so what kind of spanning tree version you're running on. So you'll get more details about this. And I am running rapid spanning tree protocol here. So this comes about your IGMP. It is multicast protocol, and what kind of version I am running on, and what is the multicast address is used. We are not going to detail about that, but you can still look into your multicast protocols in Wireshark. And you can also check your layer 3 header, and it's not marked with any kind of prioritized traffic. So DHCP value is 0. So no priority for this particular traffic. And we know TLS, it's a transport layer security. And we discussed in detail about how this SSL decryption happens. And once you do the SSL decryption, you'll come to know, because after TLS, you don't see any traffic. Once the TCP connection established and if your TLS tunnel, it's an overlay on top of your TCP. So if on your successful 3-way handshake, your TLS tunnel will be established between your source and destination, and you cannot see any kind of traffic. But if you decrypt, you can see what kind of traffic, what kind of application level protocol it's being used. So in the use cases when we discussed, we have seen we have been using HTTP, and it is using a GET request. So inside that, you will drill down and you can see all your informations. So SSL decryption is very important. When you do a troubleshooting, you'll get to know about what kind of certificates that's used and what is the root certificate that's been used, and you see any kind of certificate errors. So all kind of information you can see when you do an SSL decryption. The other important thing is DNS query. So inside the DNS query, what is the main thing we should look for? So when I send a DNS query, you will see what is the authority name server that's being used and what is the query is for, and how long is the DNS TTL is used. So for most in the most DNS cache, the TTL value might be 1 minute, 3 minutes, 1 minute, and it can be extended up to 3 minutes. It's all depends on the kind of config and the kind of platform they use for DNS. So the key thing you should know about, so what kind of query I'm doing and what is the authoritative server. We discussed about that, what is authority name server. So that is the actual authoritative server which holds the record what you're looking for. So here I'm using for if I'm doing a query for record davidbumble.com, and what is the authority name server for it. So it is behind. Your records, your DNS resolver would hold those particular records. It can be an A record, or the record depends on what kind of query you try to do from your browser. So in your DNS response, what is the key thing you should know? So in the standard query response, I see no error. And in some use cases, you see some kind of server error, server unreachable. These are all the common errors you see if the DNS query is not answered. And if you're getting response with server error, there's something problem with that. So we know about this DEVRO process, discover, offer, request, and acknowledgement, and we discussed about that. So it is again a broadcast. And what kind of packet is that? It is a DHCP discover packet, and you can see your client MAC address. And since this is my broadcast address, I don't have any other information because this is DHCP discover. And in the offer message, so it's offering with an IP address 10.1.1.1, and this is my client MAC address. And I see this is this is a source 10.1.1.1 254, and this is a destination, and it's giving an address 10.1.1.1, and I see the client MAC address. And so far here, my connection is not successful. So you see in the request message, I see more information. So my client IP address 10.1.1.1. So far, I didn't agree with all this information. In the final acknowledgement field, so I'll agree for all this IP parameters, whatever you send. So in some use cases, we use a boot reply and DHCP and boot reply both does the same job, and it is just a naming convention. So you can use DHCP as well as bootp. So both are for dynamic host configuration protocol. And we all know about this VRRP. So this is it's a hot standby protocol. So for example, if you have your router something like this, and you got your switch, and if you make a redundancy something like this, and you got your VLAN 20, and this is 20.0.0.2, and this is 20.0.0.1, and we got a VIP virtual IP address that points to both, and my VIP is 20.0.0.3. So here I have configured 20.0.0.4. So I do a static route, IP route for all 20 network. So I have to go to 20,003. So that is my VIP. So what happens here, if this particular device goes down, 20,001 still points to 20,003 because that is my VIP. So from the user standpoint, if this is a PC, if I keep sending the packets, it will go like this. And if this particular goes down, it's still the packet will be, redirected back to this router because both points to the same VIP IP address. So when we configure preempt, that's something, if I want this particular device to be always an active virtual forwarder, your actual forwarder is this particular router 1, and you have to create a preempt. So it means that it kicks out the standby router and it will say, so I am the active when I'm come back, when I'm back, when I'm functional, and you should go back to your standby state because I have been configured with preempt. So this is a high level overview of VRRP, and you can see this information. You can see this particular information in the Wireshark, and you see now what is the virtual router ID that's being used. And it says default priority for a backup VRRP is 100. So your active should have an higher, the value should be higher than your default value. So here in this example, if I give a priority value something, if my priority is 120 and the default is 100. So this is my master and this is my slave. So you will see all this information inside. When you do a troubleshooting, you will go through your VRRP packets here. So if you are using any kind of authentication, you'll see that authentication should match on both devices to establish a successful VRRP, keep alive. And HSRP is an equivalent Cisco proprietary protocol. The mechanism is same, no difference. So you can also see this HSRP. You have to give a display filter HSRP for it. For VRRP, you have to give VRRP. So we know about this. We discussed a lot about this ICMP. So for the ICMP echo request, I should get an ICMP echo reply. And the key fields you have to see is identification, because for this, the identification is a unique number. For every ICMP request, your identification number is unique. And that's how you're going to distinguish, okay, this is my first ICMP packet. So this is with identifier 0x005, and it's the second, it starts with an increment of 1. And some operating system, they never give an freedom of accessing their identifiers. So that depends on the operating system what we use. And here, if we look at this is ether type. By looking into this ether type, you will say what kind of protocol is used. So we are using IPv6 here. And the ether type value for IPv6 is 0x86DD. So by looking into the ether type value, you should know what kind of protocol I'm using here. So now, if you see this particular screenshot, there are a lot of retransmission happening. It's between the server and the client, and the destination port is 80. So what we see from here is the source IP address 10.0.0.5 sends a retransmission. So it is lost on the way to the internet, or maybe the acknowledgement was not sent back on time from the web servers. So this is the retransmission. We know we discussed about retransmission, but what kind of retransmission is this? The retransmission is happening for port 80 here. So we see various destination address, and all retransmission is happening to the port 80. Because by looking into this protocol HTTP, I know all this retransmission is happening for port 80. And you have to look for something problem with the server. So who is doing a retransmission here? So the source 10.0.0.5 is doing a retransmission. So 10.0.0.5 port sends a retransmission. The client is keep sending a retransmission. So all these servers are not reachable here. So this is obviously something wrong on the internet line. So this is how you can figure out, because I send the retransmission for multiple public IP address. So it means my internet is down. So this is the one thing you have to look at when you look for your retransmission. So who is sending a retransmission, and it is sending a retransmission to whom? So if you look at this, all this retransmission is between 10.90.30.12 and 10.1.1.200. So if all transmission to a single IP with a single TCP port number, it will be a slow application here. You can see this is an FTP connection. It's trying to establish a connection from the source IP 10.90.30.12. And also, if you go to your conversation filter, you'll see all kind of the conversation that's happening between source and destination. And if you limit to your display filter, you will come to know only the retransmission happening between the specific source and destination. So you have to make use of the conversation filter we discussed, and you can figure out why the retransmission is happening here. So in this particular use case, if you look at this, you can see there is a time interval. It's all started with the 406 microsecond, then it is 220 millisecond, and it is increasing to 656 millisecond. Then it jumps to 1 second. Then it becomes 2 seconds. Then after 4 seconds, after the 4 second, again, the packet has been sent from source to destination, and there is a successful connection establishment happening. So after five consecutive retransmission, my connection establishment happens. So there is something happened in my network in the middle. So this is a network issue. So we have to figure out where exactly the problem is with retransmission. Is it a problem with my internet, or it is a problem with my network congestion? So here there is a congestion. So there is a blip in the middle, and I got the connection back again. And we'll discuss about this IO graph. So if you go to the IO graph and if you apply for any filter, for example, here I am trying to filter only the TCP stream. So the command you have to give is tcp.stream equal to 64, and the type of style I want, it should be a line. And you can give a coloring rule for the same. And here I have given the color red, and you can see all your TCP streams with 64. I mean, TCP stream 64, I see with the red lines here. And what are the retransmission that's happening? So I am using a dots to see where exactly I see retransmissions in my communication. And this is my FTP download. And you can distinguish your retransmission. We'll do this in the Wireshark, we'll see that. So we all know that the duplicate acknowledgement is something that is the acknowledgement that's been lost in the middle. And the relative sequence number is something, instead of sending the whole conversation, one day I'm sending back the missed data. So the dupax is used for it. So it's a duplicate acknowledgement, because I have been acknowledged this before, but I'm still acknowledging because you're using a relative sequence number. That's something in the middle you lost, and I'm going to send this back. So it is requesting for the sequence number 1459337. So it sent it back again, 1459377. It sent it back. So in the TCP fast retransmission, if you drill down, if you see the sequence number, so it is requesting for the sequence number 1459337. So that's been sent again. So now my connection establishment happened now. So how do you distinguish your dupax and retransmission here? So again, you can use your coloring rule. You can use any coloring rule here. So tcp.analysis.retransmission, and if you give an impulse, so it's going to show an impulse symbol, something like this. So both are using the impulse symbol. It's something like a graph like a symbol here, and you can use the filter tcp.analysis.duplicate acknowledgement number to find it. So in this, you can use this in the Wireshark IO graph. And we discussed about this. So this is a query, and this is a query response, DNS query and query response, and it took 3 seconds. And it says in the query response, no such file. So this is an error message. So who is the authority name server? It is a.dns.tw. So there is no such file. There is no such record. And if you do a DNS, and if this particular port is closed, port number 53 is closed, so it is going to refuse your connection. So your DNS server refuses a request. So you can see that in your DNS query response. So your query is refused. So you have to check something with your server, why it is refusing. Is it the firewall is blocking or something else? Or maybe the DNS server is down. So if you look at your HTTP header, so if you do SSL decryption and if you look inside your HTTP header, and exactly you can see what kind of firewall that's blocking here, that's not applicable for everything. And in this particular use cases, we know there is a problem, a firewall that is blocking this traffic. So the service is unavailable because this particular port is blocked by the firewall here. And you can see this right away inside your HTTP header. And you can see the website blocked by Netscaler firewall. This is one use case that's not applicable universally for every firewalls. And we know this of the file transfer or your shared drive, you can access your files through SMB. That is a protocol used. So here it says, if you open up your SMB protocol, and you can see this is an access denied message. So, and also you're accessing this particular directory, NAS01, it's a home directory, and you're trying to create you're going to create something inside this particular directory. So you'll get to know about all this information inside your SMB block. And if your access is denied, so you have to check something else. Why the access is denied? Is it your LDAP integration is fine, or you gave your wrong username and password for it? So using a Wireshark, you'll get to know exact reason, and you will Google it for the reason. So why it's happening. So this is all about the most important use cases with the Wireshark. You can make use of it. And now we'll discuss about Tacacs and Radius. So Tacacs and Radius. So this two, or we call this as this is used for device administration. I mean, Tacacs is used for device administration. So we'll see exactly what is the packet flow for Tacacs. So, I mean, maybe 5-6 years back, they used ACS, Cisco ACS. That is something I am aware of. And they use Aruba POS. And now this being the next generation is Cisco ICE. They call this as an identity service engine. So first we'll discuss about Tacacs. So for example, if you got 120 sites, and what happens, you have to have a username and password to log in the boxes. It can be a routers, or it can be a switch, it can be a firewall. So there are many ways to authenticate, and Tacacs is purely for device administration. And if you've got 120 sites and you got 300 plus, or maybe 3000 plus appliances, you have to create your local username and password for every appliances. So from the management perspective, it's too difficult to configure every single device. And the other disadvantage of using the local username and password is you cannot do accounting. Accounting is who logged in this box and what he is doing, what kind of commands he is executing. So those kind of accounting you cannot do with the help of local username and password. So I need a device where I can do a central administration for all these appliances. And I want to do accounting specifically. And I know who is accessing when and what is the time frame, timestamps. So you'll get to know about all this information. It's all being dumped inside your Cisco ICE. So here you're running a feature called Tacacs plus feature. So what you'll do, you will add up all your 3,000 appliances, or how many appliances you have at your site. It depends on the number of appliances you're going to use. You're going to add all these appliances. And the key thing is you have to configure your Tacacs configuration. So you have to define your Tacacs server. Example, if my Tacacs server is 10.0.0.1, so you're going to define your Tacacs server as 10.0.0.1 here. For all these appliances, you're going to do your Tacacs configuration. And the key thing is you're going to use your shared secret. Example, it is Cisco at 123. So you have to define the same shared secret for every single appliances you add in your in your ICE. So once this is added, so whenever there is an authentication, when you do authentication from your jump box, so when you try to access this particular IP address, if your management IP address something like 20.0.0.2, so there is request source, it comes from 20.0.0.2, and it will relay back to your Tacacs server. And when you type your username and password, your shared secret will be exchanged between this appliance and to your Cisco device. And from your jump box to your device is unencrypted. Whereas from your Cisco box to your Tacacs server, that is encrypted. So when somebody sniffs the traffic between these two, you cannot see anything. So the logic is simple. So they'll be running a profile. So you'll be given with privilege level 15. So that is something you can access everything. You got read and write access. So that is purely based on your policy set. So whatever the policy you define in your Tacacs. Example, inside your policy sets, you declare something like, so your network engineer group. So that is again, this is integrated with the help of LDAP. So inside your LDAP, you got a group called network engineers, and your username is something like ABCD. So when a request comes from your jump box, and if you type your username and password, so in the backend, your Cisco ICE will query your LDAP, and it will look for this credential ABCD. And if it matches inside your policy sets, you would have defined your privilege level as 15. That is shell privilege to access your CLI. So this is returned back to this user, and now he can successfully log in. And usually when you do the Tacacs configuration, it is always recommended to use a fallback option. So the first primary authentication should be for your Tacacs authentication. If Tacacs is not authenticated, or if Tacacs is down, so your local credential is used to log in your box. So if you go and if you manipulate your shared secret, and if you make a manual disconnection for testing, so you cannot log in the box using your Tacacs credential. You should log in your box only with your local credentials. So it is always recommended to use a fallback, and two key things. So what is a kind of authentication mechanism you use? Authentication, your authorization policy. So you've been given with a privilege level 15, that is your authorization. So authentication, I am using Tacacs authentication. And accounting is who logged in, when he logged in, what kind of commands he is running. So all this information is dumped back inside your ICE. And if you go to your ICE and if you look for Tacacs live logs, you will see all this information. So is it my authentication is successful, and what are the key attributes that's been exchanged between the network appliance and the Cisco ICE. And in the Wireshark, I'll tell you, so you can also decrypt this information in Wireshark. So for that, you have to go to your Tacacs, edit, preferences. You have to go to your protocol. You have to go to your Tacacs plus. So you have to give your encryption key here. So once you do this, you can decrypt your Tacacs. So we are not doing decryption here. So here it is just a query and I get a query response from this server. So authentication, authorization, and accounting is not configured here. So authentication and authorization is successful between the source and destination. So all an encrypted reply. So this is a server because the port number used by the server is 49 and this is a random port generated by the PC. And I got a reply from this server for authorization. So you can verify that. So all this is a request from the client 192.168.1.32 and 192.168.1.5 is a server. So it's giving a response for the authentication. And if you decrypt, you will see is it your connection is successful or it is failed. So for every Tacacs authentication, it uses a session ID. So I can see the SYN/SYNAC and ACK here. So my connection is successful. So once the user typed in and he finished everything, he sends a FIN and I get a FIN-ACK from the server. So it's a gracefully closing this connection. So this connection is successful between client and server. I come to know about this. Source port is a random port 59087 and for the destination is a server, it's 49. So this is not about deep dive about Tacacs, but this is the packet flow and we'll see how the packet flow looks like inside. So if you see this, so this is a device, network appliances, we call as a NAS. So all your user traffic to the NAS jump box, if you log in, so that is not encrypted, but from the network appliance and the Tacacs, all this information are encrypted. So it's going to send an authentication request and I get an authentication reply back with authorization level. If you're given with 15, that's a full access. And if you got write-only access, read-only access, sorry, your privilege shell value will be minimal and you cannot do any changes with the devices. So then again, authorization request where your shell privileges will be exchanged. In the authorization reply, it's going to say your privilege level is 15 and it's an accounting packet again. So or whatever the commands you run on this particular devices, that's been dumped back inside your Tacacs logs. And the server uses a port number 49 for the same. So all your passwords, username and password will be encrypted. So this is called this three process. I mean the three key the three key parameters used are authentication, authorization, and accounting. And it is a central management for authorization configuration. That is the main use of it. And it is used for network administrators to access the device. In the same way for device administration, we can also use a radius authentication. So it encrypts only the password and it uses a UDP port 1645 and 1812. And it depends on the operating system. And every network device should have this authorization configuration that should be done inside. So that is applicable for both. So you can also configure active, passive, or maybe failover scenarios. Example, you can configure both Tacacs servers. It depends on the deployment. If primary fails, the request goes to your secondary. So you have to create a Tacacs group and you have to define your primary and secondary for the same. So both does the same job, but here only the password is encrypted. Here your username and password both are encrypted, and there is very minimal vendor support for Radius. And for if you have an eyes for your controller and for other purpose, then you can definitely make use of Tacacs. And if you want to see the config inside, as I said, you should give AAA authentication login, and you have to give your Tacac group if you have multiple Tacac servers inside. And this is a group, a Tacac server, and this is the IP address of it. And if you're using a shared secret, you have to define your shared secret key inside. And AAA new model is for Cisco appliance. This is a key command to enable your AAA authentication. That is, if it's want to support authentication, authorization, accounting, you have to enable this globally. Then you have to define your Tacac server. Then followed by that, you have to define your Tacac server name. And in the authentication group, the first primary group is your Tacacs group, and if it fails, it has to look for your local credential. And you have to define this under your terminal connection, VTY, virtual terminal line, and you have to define your authentication policy inside. So this is pretty simple config, and for accounting, you can define your authorization levels. So I have to do whatever the commands, it starts from privilege level 1 to 15, whatever the commands you use, that will be the accounting information will be dumped back to your Tacacs server. So this is for the Tacacs authentication. And when you use, when we talk about the Radius, and if you use any kind of certificate-based authentication, let's come for the Radius. So the very first message, it starts from the client is EOPL. It's over the LAN. It is extensible authentication protocol. And if I send an EAP request, so all this information is not encrypted between the client and server. So the EOPL packets is only between the appliance and the client in client. And the Radius request is from the network appliance to the ICE, or maybe whatever the authentication server use. So this is generally a Radius access request, and you get a Radius access challenge message. And again, the appliance will send back the Radius access request again, and I'll get a Radius access accepted message. So you are authenticated and you can access the devices. So in the EOPL, we are not going too deep about EOPL here because it's primarily for Tacacs. And if your EAP message is successful, that is something you have to configure your EAP, and your port should be open for EAP. Only after your successful EAP communication, all your data traffic and other traffic will be exchanged. So this is about Radius and Tacacs. And the final piece we want to discuss about today is how when we have a problem with a slow throughput issue, so how we are going to find that. And along with that, some of the graphs we make use of, and we apply some filters. Let me open it. So this is one of the window problem we got. We discussed about calculated window size. If your window size is squeezing, there is something problem. Then the amount of traffic that's going to receive, that the buffer is squeezing. So you'll definitely observe the slowness and throughput issue here. So if you look at this particular capture, and if I drill down, if you look at this particular the window size, and if you go to scaling factor, you can see this, right? So in the scaling factor, you can see it's decremented, it's -1. So if you see the previous window size is 65,160, and if you differentiate this, if you go to this particular packet, so my window scaling factor is not increasing at all. Why is that? We seen in the early, in the normal captures, the window scaling factor should be incremented. And we see that how exactly the calculated window size is calculated before. But here it is not incrementing. And if I keep drill down this, and I see the being squeezed out and no data is exchanged, and it is just 3,567. And if I go to statistics, TCP stream graph, and if I go to Stephens graph, so you should see a ladder-like option here, and it should be continuous, something like this. So here there is no choppy traffic, but if you see there is no traffic that's being sent. If you see in the middle, there is no traffic, it's being sent. So it should be something like a steep ladder that's going towards upward. So this is here, this particular time frame, I don't see any traffic that's going between. So this is because of a window size problem. So using the TCP Stephens graph, you can find. So if you try to find any other captures, I go to my PCAP. And if I look at this, if I go to statistics, so if I zoom, this is not actually a huge number of packets that's being exchanged. Let's go to a PCAP. Let's see this VoIP traffic. Here we are not using TCP. Let me take any other capture for it. EBGP, this is TCP. So I think this is all very minimal statistic. So that is especially for upload, download. If you do a live capture for it. It's all not really in application traffic, it's all encrypted. Let's do a capture. It is generally, it is used for your upload and download. You should say send really a huge amount of traffic. Set something, I'm establishing a connection. Let me do an IPUF. So my command prompt. CD. What is that? dir -c. Of public servers. If I go to this BizNet, where is my command prompt? So what's happening here? Can I capture is running? I have to go to my live capture. If I ping it should be between port 5201 to 5203. By 201. Is that I cannot define the port. Should be okay. Default is 5201 and that is -p. Device is path parameter. Oh, I'm not establishing a connection with it. Let me try to disable my antivirus. Let me disable my protection for 1 hour, 30 minutes. Yes, let's try. So I'm sending a retransmission back. This takes. It should be something like this. It should be a upward traffic, but we are not setting much traffic, so we cannot log any kind of information. So zero window problem from my, okay. Let me stop this capture. H. So this is a TCP zero window problem from my browser. Okay, so let me take this, copy this, go to statistic, TCP Steven graphs. And if I go to stream index is 40. Okay, stream index is 40, that's fine. So I'm trying to push the traffic, but it's not going from my PC now. It's not establishing a connection. So generally it should not look something like this. So if we successfully establish a connection and the window problem, IPerf would be the better way to do so. So now I cannot establish a connection with the server, so maybe the server is busy and it's refusing the connection. So it should not be something like this. So it should be like this. It's always to be a steep line without any drops, choppy traffic here. So with the TCP Stephen graph, you have to use this when you have some kind of a throughput issue, something like this. It could be a TCP window size problem. It can be your network problem. So especially for your throughput related issues, you can use of Stephen's graph. And we discussed about the flow graphs, between source and destination, what kind of connection I use. And if you go for display filter, you'll get to know about what are the conversation that's happening between source and destination. You'll get more insight about that exact packet flow. Then the other thing is protocol hierarchy. There you can see what kind of protocols you're using here. So I'm using TCP and IP, and what is the amount of packet that's being used. So mostly my IP traffic is used, and my TCP, there is no UDP communication here. You'll get to know about the complete insight of what is happening here. So that's it about the graphs, what we use. We can make use of this. And herewith we have covered everything.